This last chapter that we're going to cover deals with scaling, or rather similitude. That is, how do you take something at one size scale with certain performance metrics and bring it to a new size scale and maintain those performance metrics. So I'm going to give you a list of quantities that we're going to encounter during Chapter 7 that have to do with scaling. First is an industry agreed upon definition of when threshold is reached. So the standard that we will go with is that the gate source voltage is at the threshold voltage when the current passing through the drain equals 100 nanoamps times the channel width divided by the channel length. It's just an industry factor defined based on just how curves tend to look. Second thing in my list of almost random facts about Chapter 7 here is that the bulk charge factor is going to have a new name, but it's the same thing. So there's still a body effect, which means that you still have a situation where if the body is at a different potential than the source, we have capacitive charging inside the body. It was called M in Chapter 6, and in Chapter 7 it's called Eta. There may be a reason for the name change, but I'm not tuned into what that reason is. So when you encounter this Eta, keep in mind that it's 1 plus the depletion layer's capacitance divided by the oxide capacitance. And then it gets used fairly right away when we derive an expression for the surface potential, which we're going to do. You can rationalize it pictorially, graphically, but we're actually going to derive it. The surface potential is really the gate source voltage minus flat band voltage. Deal with the bulk charge factor later. And when the gate source voltage equals flat band, you have a flat band. Any change of the gate source voltage from that voltage level bends the bands. And so the amount of band bending is the difference between whatever the gate source voltage is now minus what it needs to be to have a flat band. But you divide it by the bulk charge factor to actually have what that surface potential will be, to account for the fact that the body might actually be at a different potential. So there might be charge beneath the depletion layer. We're going to talk about the surface concentration of carriers, and it will be called N sub S. As you change the gate source voltage, you bend the bands, and you establish a surface potential. Hopefully it seems common sense to you then that the carrier concentration is going to go as e to the minus surface potential energy. Just like it goes as deep inside the bulk, it goes as e to the minus E conduction minus E Fermi. At the surface, it'll go as e to the surface potential. In Chapter 6, we dealt with the IV model, but I want to emphasize that that was above threshold. We didn't talk about what IV looks like when the threshold voltage has not been reached. That is when the gate source voltage is very low. It's a different behavior. We will talk about that in the next lecture, actually. And we will come up with an expression that kind of makes sense. It's exponential in gate source voltage. If you take that industry standard I talked about there, that this is the drain source voltage when the gate source voltage equals threshold, you can figure out the proportionality constant then in terms of threshold voltage. And so we have equation 727 that you'll be able to rely on. Something I point out is that there's going to be a lot of this going on. Log base 10 of E. There's this practice that we're going to have to deal with where we have expressions that may have been exponential, but we do graphing on log with log base 10. And so there are a lot of cases where we're going to need to convert between log base 10 and log base E. So you may just want to get used to this constant factor here, log base 10E. Now when you take the gate source voltage to 0, you have what we'll consider the off current. That is, when the gate is set to the same potential as the source, that's like delivering a 0 in digital logic, a 0 to the gate. And so that's the off situation, because in CMOS you either have 0 or high voltage at the gate. The current when the gate source voltage equals 0 is simply this expression up here with gate source voltage set to 0. And I unpacked the exponential and wrote it instead of as log base 10 of I just wrote I. And something I point out is that the exponential then has this minus threshold voltage, gate source is 0, and then we'll just call it big S, all this stuff together. So this big S becomes a figure of merit for a MOSFET. If you look at this expression, the drain source current will change by a factor of 10 for every 0.06 times the bulk charge factor change in the gate source voltage. So this is a fact. This point number 7 here is just a fact that the drain source current changes by a factor of 10 for every 0.060 eta change in gate source voltage, but that gives rise to the figure of merit, which is the sub-threshold swing big S, which is KT over Q divided by log base E and the bulk charge factor. Everything besides that comes out to just 60, so 0.026 divided by log base 10 of E is 0.060 volts, or 60 millivolts. This is a phenomenon that we're going to address a lot, because this is what ultimately has been limiting MOSFETs, is a drain-induced barrier lowering of the threshold voltage. Inside the channel, from the drain to the source, there is a potential hill that carriers need to overcome in order to pass through the channel. And that potential hill has to be controlled. As you make channels shorter, that potential hill goes down, which essentially means the threshold voltage is going down. And it goes down as the length of the channel. We don't want it to go down. We want to have a threshold voltage that we have always been able to have. That's the whole idea of scaling, is you make your device smaller without changing the performance metrics. And you don't want to make the threshold voltage really small, because then you end up with a larger off current. You notice there's this script L sub D in the exponent here, called the DIBL parameter, drain-induced barrier lowering parameter. We're not going to show it. I'm just going to give it to you that it's the geometric mean of 3 important depths: the oxide thickness, the depletion width, and the junction depth, which is the depth of the drain region. So those are 10 things that we're going to encounter in Chapter 7, listed out not entirely in random order. I think it kind of goes in that order. And we'll begin that with the next lecture.